Well, we'll do something fun today. We'll do cybernetics. At least that's how big my life is, right? That cybernetics is fun. Okay. Do you have any questions for me before we get going? We are in cybernetics tonight, and there is to be offered next semester, I believe now on Tuesday night, not Thursday night, a special topics on cybernetics and organizational learning. So I'm going to be teaching that, and so you might want to avoid it. I don't know. No, but it's fun. It's good. I've taught. Melissa has taken my special topics on the system. You made it good on Peter Senge and his writings. And the way that we think about systems and organizations and adaptation of organizations and organizations that become dinosaurs and don't adapt. So we had a good, and autopoiesis, that's the word you ran into at least a couple times, which means self-organizing, that it creates its own organization. So I think what Christine is looking for me to do next semester is to do something on learning organizations, which is the idea of an organization that's continually in a learning mode, where every part of it is in a learning mode, and that the organization as a whole then learns how to produce its results in a different environment. The idea that as environments change, organisms have to adapt to the new environment. And so it gets into Darwinian concepts that could apply to organizational life and selection and variation, selection and retention and all these things. So it's a nice class, it's a nice topic. So think about that. All right, I'm going to start then, and we'll talk about the word cybernetics itself. I hope that you're reading the introductions in Craig's book. I really didn't assign it, but it helps make sense of all the articles when you read the section, if you read the introduction there. Cybernetics is a very big field. It's a very big field, and it's divided into distinct groups that are sometimes called hard or soft. So the hard ones are your people who do modeling, computer modeling of systems, and do quantitative measurements. You read an article in Craig about that, where the woman was going on, and like the thing about brain processing power and message capacity and memory allocations. That's kind of a hard, what we call a hard approach to cybernetics that looks at information and how information works its way through a system. But there's a soft side to it too, which is more looking at adaptation and relationships, and the way relationships adapt around certain rules or organize themselves. So there's both hard and soft approaches to cybernetics. The origins of it, though, the word, we often think of robots. I don't know if you do when you think of cybernetics. You think of cyborgs or things like this. It is an old word, though, that comes about, and it's about the issue of control systems. So how do you control something to make it do what you want it to do? So the person who steered a boat in Greek language, on the Aegean Sea there, going between all those little islands, was called the Kubernetes, or the steersman. And so the kuber word means to steer or to control. So part of this is the idea of control mechanisms and how they work. And so, for instance, I want to do just two examples of control systems to get us into thinking about how information and feedback function in systemic ways. So the first one is pretty simple. You have your room in your house, and you want to keep the temperature at a certain temperature. right? So we'd like to control the temperature. Now, you could do that. Let's say you want to keep it at 70 degrees. You could do that directly by having a thermometer, and then every time it got below 70 degrees, you could light a fire, right? And burn that for a while. And then it would get hot, and then you pour water on the fire and turn it off. So you can manually control the temperature. But what you would like to do is to establish some kind of an automatic system that will do it for you, so you don't have to do it. So in order to establish an automatic system, there's a number of things that are going to have to happen that you are doing, but you want to automate, or you want to set up so that it functions on its own. So for instance, if I'm in a room with a thermometer, that thermometer is a sensing device, right? That senses the temperature in the room. Now, I am also getting input, so I'm in a device of sorts that's getting input from the sensing device. So I have a thermometer that senses, and it's, how does it send me an input?
Visually?
Visually, it has a tube, and it has numbers on it, and so there is an input that comes to me from the sensor. I get the input, and I process the input. Right? What I see it, and inside my brain it says it's below 70. It's time to get the fire going. So now I receive input, and I do an output. I go and I light the fire, which is my output. But from the wood's perspective, that's an input, isn't it? The fire coming to it is an input, and its output is to burn. So what we've got is this whole system of interconnected inputs, outputs, input, which becomes an input, which becomes an output, which becomes an input, becomes an output. So there's there are elements that are receiving input and giving outputs, which becomes the input to the next thing, right? So we're just trying to learn to think in these languages, in these terms. This could be an organization where someone gets something and then they speak, which becomes an output of them, but it becomes input to the next person who hears them, and so it just cycles. So now, and then the sensor, I watch the sensor, and the sensor goes up to 70, and then I pour water. So it signals me again. It has an input, I have an output, I pour water, the fire gets the input, it goes out. And the temperature stays somewhere. Now, that's a pretty inefficient way of doing things, right? So we don't do it that way. So what we do is we put a little box in our house. It's called a thermostat, right? Now, that thermostat is a sensing device that provides information about the environment. It tells us where the temperature is, right? So it's connected by a communication channel, a wire, to a burner unit, an oil burner or a wood stove or whatever you have. And this sensor unit communicates information to this unit, which then goes on or off and has an output of hot air or water, hot water or something, which goes into and affects the environment, which in turn affects the thermostat. And so in effect, what you have created is a loop. You've created a loop, a control loop. And as this continues to sense, it sends signals, input, output, temperature goes up, it signals it turn off, turns off, and the cycle is complete, but the cycle is continuous. As long as you pay your bills, it works. The system works. All right, so let's stop there. right? So you have sensors, you have information, you have channels across which information flows, you have inputs and outputs. This is a language of cybernetics, control systems. And this is going to affect families, it's going to affect organizations, it's going to affect international, structures. This simple model is going to affect things. Now, let's talk about this for a minute. How often does this system cycle? Or how often does this thing go on and off? Let's just put it pretty bluntly.
You're not asking when does it go on and off?
Well, how often?
Isn't it always on, technically?
Well, the system is always sensing, right? It's always in gear. But what I'm getting at is it's 70 degrees. This system has shut down the burner. When does it go on?
When it's 69 or 71?
When it's 69.999 degrees. So let's assume for a minute that that's the case, that it turns on at 69.99 degrees. So off we go, turns it on, temperature comes on, it gets to 70 degrees. How long does it take to go from 69.99 degrees to 70 degrees?
It depends on the environment.
Depends on how big it is, whatever efficiency, but probably not too long, right? A thousandth of a degree, it goes up. How long does it take to cool down a thousandth of a degree? Probably not too long either. So you could be in a situation where this thing is going on and off every 20 seconds. Do you want this working like this? Do you want it to go on every 20 seconds or every 10 seconds? Or is that bad for the system? Would it be better for the system if it went on for a while and then shut down for a while? Right? What do you think? Probably for the thing, it's better that it goes on for a while and then off for a while. What do you have to do in order to change that oscillation? We call this an oscillation when a system is continually making corrections, and it can actually overcorrect if it's oscillating too much. We'll talk about other forms of oscillation where it goes back and forth very rapidly. So how are you going to change the possibility that this heater could get in an oscillation that could damage it somehow?
You could have it heat up to 73.
Okay.
When you say 70.
Okay. So you could change the parameters. You could change the rules of the system, which would prevent an oscillation from taking place. And so you could say, all right, the rules that are embedded in the sensor are turn on when it's below 70 and turn off when it reaches 73. Now you've created it. It goes up to 73, it turns off, and it takes maybe a half hour, an hour to get colder. And then it goes on for 10 minutes and goes off for an hour. That's a more, sensible pattern. Although I just saw a television commercial for a modulating heater. I don't know if any of you saw this. It was pretty interesting from a cybernetic perspective. Is what they did was they designed one that it works with the sensor to maintain, not from 70 to 68, but to maintain it at 70. And so it's got a computer and it calculates the rate at which it's sensing that things are changing, and it turns itself on and turns itself off, and it just keeps your temperature at 70. But it has, so this is a new kind of a control device and a heater that is structured not to, break down because it's going on and off real rapidly. Things are sometimes not designed to do that. They're designed to run for a while and then be turned off. So it's interesting. They call it a modulating heater, and I had to read up about that. But anyway, you get the sense here that if it's a poorly designed control system, you can end up with a rapidly oscillating response, and it could be annoying or it could be damaging to the system. In relationships, this is kind of like the situation where someone has a low tolerance for feeling separated from the other person in the relationship. So they have a very narrow range of how they feel comfortable in a relationship. And so if they feel like the other person is a little far or not communicating enough, they kick in turns on the system, and they want to say, is everything okay? Are we good? You know, I'm feeling a little separated here, you know. Everything okay? Yeah, everything's okay. Okay, I got my message back. But then it goes down 1/1000th of a degree, and the message kicks in again. What does that do to relationships where it's constantly, you know, checking? Are we okay? Everything okay? You oscillate real quick, right? And that doesn't go well, right? You need a little more tolerance. You need to be, you know, very close sometimes and far apart. But it's not an emergent, you know, you don't turn on the system until it ranges somewhere else. So you get a feel for how relationships are systems too, where we sense things. If it's out of the range we want it to be in, we send an output that becomes an input to something else that we expect to do something to bring it within the acceptable range. This is the way cybernetics thinks about things. And so you think about oscillating systems, control systems, or systems that are circular, loop systems. You set them up, turn them on, and they run. And they keep things going. All right. Let's do another example, which is one of the actual examples from the early days of cybernetics, which has to do with ships and ships being threatened by airplanes. And they have guns on them, right? Have these 50 caliber machine gun things on it. And the problem that you face is you have to shoot down these airplanes before they blow you up, you know, in the Navy. And so you can do this a couple ways, right? One is that you can put a person behind here who controls the gun, turns it on, turns it off, you know, pulls the trigger, puts the finger off the trigger, turns it up and down and side to side. That's one way you can manually control it. That depends on the operator paying attention all the time. That depends on their skill. That depends on, you know, if they ate a bad hamburger the night before and they don't feel good. Humans are very unreliable as control mechanisms, as sensors, because they're always changing. Things are changing. So the question becomes, can we automate this system? Can we create a loop that will control this, and we can just walk away and it will do it itself? Can we do that? Well, that was the question that early cybernetics people were struggling with. So let's think about this. What do you need to do in order for this to work?
I think one of the bigger problems that would come from creating a system that controls it automatically as opposed to with the human is identifying the airplane and making sure it's actually
Okay.
an aggressor.
So we need an ID sensor that will somehow identify friend or foe. Okay, so in our system, we have to have this that will either turn the system on or turn the system off.
And how can we also be sure that it's always going to work? I mean, we're computers, they always go down. You know what I mean?
Okay.
Can we be sure that it's always
So if we want to make sure this works, we will have to create a redundant control system where if the first one fails, the second one fails, because the probability of both failing is lower than the probability of one failing. And maybe we'll create 3 or 4 levels of redundancy in our system. So we will, so check, we've got to have a redundancy because this is a big deal. What else do we need?
Isn't there a need for a decision mechanism or
What decisions have to be made?
deciding on whether to actually shoot or alert the airplane or threaten it first or ask it to leave the perimeter, or I guess there are several decisions to choose.
Okay, so there are a number. Let's assume for a minute that we have this, the captain has decided, turn on the system if anything comes in our area and doesn't signal the right signal, we're going to shoot it down. So we'll have made that decision. Okay, we'll put a human in charge of that decision. So Ben.
No, but I was also going to say there maybe some human overlooking the whole thing, just to make sure, as Laura was saying, and also that the machines don't like spin around and start shooting the boat.
All right, so we need parameters then. We need to say, you may turn this far, but not that far. So you have to set limits on it, which are normally done by putting welding steel bars there so the thing can't turn that far.
I guess it would kind of go with parameters is measuring the accuracy of the shot, because there's a lot going into shooting bullets in general.
Okay.
The wind, the direction, and where the plane's coming from,
Okay.
the trajectory.
So we have to detect somehow success or failure. We have to be able to somehow detect, okay, we're shooting to the right of it. That means move the gun to the left, or whatever. So how's that right? If we're shooting to the right of it, we have to move the gun to the right. There we go. No, we have to move the gun to the left. Okay, so we have to detect the success or failure, and we need to feed that back into some kind of a motor, right? We need a motor that will move the thing. So we've got to have feedback from the actual event. We can't just set it to say, okay, do this, then do this, then do this. Because we don't know where the plane really is. This was the debate by the way, I think it was the phenomenological article about Spinoza and the monads. I don't know if you remember reading that article or not. But it was the idea that people interact with each other. I mean, he actually came up with an idea that people actually don't interact, that they're just so well scripted from birth to death that they do where they're supposed to be and saying what they're supposed to, without ever really coming into contact with the other beings. I mean, you can think that, and he thought that. So, but anyway, you've got to have reality checks here. It's got to be feeding back somehow. So we need a motor that turns it around and up and down. So we need motors that are instructed by signals from some coordinating device.
If you're going to have somebody getting feedback, so are you going to need a decoder then who is able to interpret the information?
Yes. So how are we going to sense that? Well, we may have, again, we're going to have a radar sensor that's going to tell us distance, and we're going to have a computer that calculates, well, distance means this, that, and the other thing. And then we're going to have some kind of a visual way of seeing maybe an image, and then we've got to interpret that image for some machine to say there's a distance between this and close that distance. All right, so we're going to have to control. So this gets highly complicated, doesn't it? Right, and to create redundancy in it, to create feedback loops. The simplest way is to say I've got to have a sensor that will give input to the motors that will control the directions and the triggers. That's the simplest way, but there's a lot that goes on. But nonetheless, you have a number of interacting parts, right? You have a complicated set of interactions and messages going back and forth, checking, coordinating, getting feedback. You have input, you have output, it shoots, you get feedback that says you're missing, which becomes input that says move it, which becomes output, which becomes input to the motors, which then moves it. And and so on and so on. So you set up this system with sensors, decision moments, rules. If it's this far, put it this high over the thing, and so forth. And you have to interpret, you have to decode and encode signals so that each unit can understand it. So this is cybernetics. And all of these things can be applied to people in relationships, small groups functioning, organizations working, and international events. You can think of it in this language with these terms. Now again, let's talk about the oscillation question here. Again, this can happen. Let's say the signal comes, you are too far to the right, move to the left, right? So the motor activates and it moves to the left. And it moves through the target and it moves too far to the left. So then the signal then comes back to it, you're too far to the left, move to the right. So it moves back to the right and it moves too far. And it just keeps, and it starts getting like this. It starts getting signals like this, right? What's going to happen? Aside from you're going to get shot to pieces because you didn't get the airplane, it's the thing's going to break because it's just going to, and you can get into what's called an oscillation that gets greater and greater. No, you're way too far to the right. Move to the left, quick. Well, you're way too far. And it expands. The commands get stronger and stronger, and it just keeps going wildly, oscillating wildly. So what you have to do is you have to overlay rules on top of it that say, if you move, only move this far and then retest. Or if if a message comes and you're moving back and forth too rapidly, stop that and only do this. So you build on top of that system other rules that if this is the case, then this. If this is the case, then this. To build in the ability, because cybernetic systems can oscillate when they control. It says, go this way. No, don't go that. Oh, go back, go back, go back. Go this way, go that way. So you have to, unless you have your information coming very rapidly, then you'll prevent the oscillations, right, from taking place. All right, so all of this language becomes the language of cybernetics. You have input and output. You have information. It has to be coded, encoded, decoded. It has to be communicated across a channel. And there have to be decisions and rules about how that information is processed. So this is at the root of we talk about redundancy, which is the idea that not only in a control system do you need to account for possible failures of the system, but also you have to deal with the fact that the information may not be adequate for the control, what is needed by the device. And so, for instance, the way this works in a telephone or a cell phone is you may be talking to someone on a cell phone and you're far away from the cell and you're getting a broken up signal, right? You're still getting information, but you're not getting enough clear information to decode the message. And so there has to be, so what do you say? You say, will you say that again? Right? Will you say it again? What are you asking for? You're asking for another transmission of the information so that you can reduce the ambiguity of what you are not sure about. So you need more clear information to come across the channel for you, which is the redundancy. How many different ways do you need to hear it before you have what was intended to be communicated? Now, in organizations, we talk about this need for redundancy in terms of people sometimes need to hear something, what do we say, 7 times before they get it, right? And that's a cybernetic point then, that you need to put it in the company newsletter, you need to have people talk about it face to face, you need to put it in the handbook, you need to put, why do you have to do all that? Because you need redundancy where the same information is given so that the message is clearly received. Thank you, I appreciate it. So here we go. So we did the thermostat, we did the Navy gun. Let's just do quick Shannon Weaver model to make sure we're all familiar with Shannon Weaver. We just did thermostat, and this will all be familiar for Melissa. Yeah, anytime you want to throw in something, Melissa, of course, you just go ahead.